This is on the bottom of your lecture notes. Like the bottom section down here. Yes, we know where we are. Okay. So anytime you're dealing with pH, you have to write out a balanced chemical equation out. And this is an acid, so you have to write out an acid dissociation reaction. So an acid dissociation reaction means it's just reacting with water. So acid plus water yields something and something. What was the acid of choice here? Acetic acid. So formula? HC2H3O2 plus water. This is an Arrhenius acid. What is Arrhenius acid? What do they produce in water? H3O pluses, right? So this H pops off, donates itself to water. H3O plus. Our marker's up again, leaving us with what? C2H3O2. Can't do it. It's bad. It's real bad. Okay. I like that this is on the video as well. Okay. Okay. So what was our beginning concentration of acetic acid? 0.5. And so you have to create an ice box. I means what? Initial, C, change, E, equilibrium. So the initial concentration was 0.5 molar of acetic acid. What's the Ka value for acetic acid? 1.8 times 10 to the negative fifth. Small or large? Small. What's the small Ka tell you? Strong or weak? Weak. Definitely weak. It's like that one only dissociates about 0.5% of the time. Not even a whole percent. So like strong acids have 100% dissociation. This one has 0.5% dissociation. It's really weak. So that's why we write the reversible error for dissociation. Okay, so this is gonna just a tiny bit of that's gonna change. What do we call a tiny bit? We just call it X. Okay. I don't know what X is, but I'm going to be solving for X. So a smidgen of the of the acetic acid will be changing. As reactants react, we add to the products. Yes. As we take away reactants, we add them to the products. Balanced chemical equations, law of conservation of mass. So I'm going to add. There's a 1 there and there's a 1 there. So I'm going to add a 1x here and a 1x here. But what am I adding this x to? The initial of what? Which is 0, right? Because usually you start off with 0 products before a reaction begins. So then we have 0.5 minus x at our equilibrium, and this is just, a simple subtraction. I'm going to draw my boxes. You can see that this stuff belongs here. Do I care about water? No. Pure liquid, so we don't even mess with it. This right here is aqueous, so this is just x, and then 0 plus x is also just x. So this is just addition down the columns. It's sometimes helpful to write the little columns for yourself. Okay, so now, what do I do with this? I have to do what? All right, what's the formula? What do you mean? So what's your setup first? H3O plus, so products, and then, oops, C2H3O2. So there's products over reactants, which is C2H3O2. I don't put water because it's a pure liquid. Okay, so then this is called the equilibrium expression, so I can only plug numbers from equilibrium, this box, into these concentrations. So this will be x times x over 0.5 minus x is equal to the Ka value of 1.8 times 10 to the negative fifth. All right, how do I solve for x, or how do I make my life easier? What's that called? What am I doing? Neglecting x. I must have said it. Thank you. I'm going to neglect x, and the only x's I can neglect are the ones that are plus or minus. So there you go. Assume that x is so tiny that we can ignore it from that big humongous 0.5 it's being subtracted from. That makes our math like a piece of cake. X squared over 0.5 is equal to 1.8 times 10 to the negative fifth. How do you solve for x? Do it. I don't want to square root just yet. Multiply by 0.5 and then square root, right? So when you multiply by 0.5, I don't know, 9 times 10 to the negative 6 and square root 3 times 10 to the negative 3. Somebody check that for me. That's right. 3.3. X is equal to 3.0 times 10 to the negative 3rd molar. Now, what the heck was our question? What's the pH? We've solved for X. Woohoo! Pat on the back. What is X equal to? That was important previously.
H3O.
Right, so this is equal to concentration of H3O plus. Now, aha! Why is X important? Right, because pH is equal to negative log of hydronium. In this case, hydronium is 3 times 10 to the negative 3rd. So what is that, like 2.52? Thanks. I can usually estimate-ish, but not get exact. 2.52 it is. Alright, who got that and understands it? Hands go back down. Okay, yay! Okay, let's do the KB one, which is a base, because on your test you have I think I give you one acid and one base. I know for sure there's a base. I think I actually put ethylamine, but we'll have to double check. Alright, I will go back in just a second. Number 2, 0.2 molar of ethylamine, weak base, 5.6 times 10 to the negative 4th. Okay. I'm telling you right now, you will see this on your test. Just start by test something. You will see this. Not the same numbers, but the same process. Has number, no, there's only 6 free response questions, 1 of each type that we're doing. So like there's one just easy K box or ice box, or just solving for K. There's one KA, there's one KB, there's one KSP that we're doing today. I think that's it. I think there's one more. All right, so number 4 said for us, we had a KB of what? 5.6 times 10 to the negative 4th. We're given ethylamine. Do you guys know the formula for ethylamine? No. Okay. Some of you don't know it. Let's just call it base. Can we just call it base? Is that cool? Okay. Because it's a base and it says it's a weak base, so it makes life a little bit easier if you don't have to write out the formula because it looks kind of scary. Base. This is still a base dissociation process, so this is still base plus water, just like we previously did. What's the job of a base in water? Really what? To make OH minuses or hydroxides, right? So this is going to be donating an H to B. So it's going to make HB plus, because remember it forms a proton, so positive charge, leaving behind OH minus. So this is just a generic version, and I'm fine with you doing the B. If you want to write out ethylamine, that's totally fine as well. All right, so we are asked for the pH, and it gives us 0.2 molar. Okay, what do I need to set up now? Icebox. So I always leave room for an icebox right under my equation, so I don't have to write it like a bazillion times. 0.2 goes where here? Under the initial for B, for base. All right, that's a weak base, so just a tiny amount will dissociate. So how to represent that? Minus X here, and then do I care about water? Nah. Okay, what else? So I start off with 0 of each of my products, because I don't start with products, but then I make products by adding plus X. If this happened to be a 2 here, what would I add? 2X, but that's a 1 coefficient there. So plus X, so then we have 0.2 minus X, X, and X. Yay, from to equilibrium. Now how do I proceed? All right, so products of reactants. This is a K what though? KB, okay? So KB is equal to HB plus times OH minus over B. Is that it? Yeah, because this is a pure liquid water again. Okay, and this equals, I'm going to go ahead and plug in my values. X squared, because that's just X times X, yeah? We're cool with simplification real fast here. X times X, and then this right here. 0.2 minus X, and that was equal to our KB number of 5.6 times 10 to the negative 4th. Okay, what do you want to do again? All right, what are our criteria for our 2 criteria for neglecting X? So it has to be true so that we can simplify our math. All right, so a small value for K and only the ones that are added or subtracted. So I can't neglect these X's, so assume that X squared is 0, the whole thing's 0. That makes no sense because it says it's equal to this, which is almost 0. But that's okay. All right, so 2 things are true. Yes, a small K, and yes, I can neglect only the ones that are added or subtracted. So then we simplify X squared is over 0.20 is equal to 5.6 times 10 to the negative 4th. How do I solve for X? So that times 0.2, I don't know that one. Square root of that. This is the answer. Say it again.
Oh, you want that?
Answer, yeah.
1.05.
So 1.05 times 10 to the negative second for x. Did we get that? For those of you who got it. This right here is equal to what significant ion? OH, because that's what our icebox says. OH is equal to X. So if I have OH, what can I automatically solve for? POH, right. So POH is equal to negative log of 1.05 times 10 to the negative 2. So POH is equal to what? 1.97. Thank you. So what's pH? 14 minus 1.97. Do it in your head. 12.03. Thank you. You can do that. And then you ask yourself, does this pH even make sense? Okay, when it's a base, is it a strong base or weak base? Nah. It said ethylamine was weak. Right, so strong would be like 13, 14. We're at that kind of like middle area, so truly it would be better if it was closer to 11 or 10, but I can't control it. It's 0.2 molar, so it's somewhat concentrated. All right, give me a thumbs up if you understand the base version. All right, most of us are okay. Some of us need to stay for tutoring today or tomorrow. All right, this is the next bit here. Oh no, I need to do the problems you're working on. Which one am I working on right now? 5? Do I need to do both of them? Yeah. Okay. I'm working on number 5. Work with me so you guys have some things to look back at. Okay. Given this reaction, 2 nitrogen, what's the name of this? That's only if it's an ion. What's the name of this, guys? That's nitrite only if it's an ion. It's a gas. Nitrogen dioxide. Nitrogen dioxide yields to 2 of these. What are these? Nitrogen what? Monoxide and oxygen. Okay, so these are all gaseous. Any of these that I exclude? No, they're all good. Okay. Calculate KEQ. So my question is, what is KEQ? If the reaction starts with, so the starting point would be initial, right? Starts with 3.0 molar nitrogen dioxide, and at equilibrium, only 0.5 of that remains. So at equilibrium, only 0.5 of that remains. Well, what was the change? 2.5 was subtracted. If I didn't know the math, if I was like, I couldn't do this math, I wouldn't call it a specific number. I would call it some amount of x's. How many x's would be subtracted from the reactant? 2x, right? So that's because there's 2 coefficients. So truly, I'm minusing 2x, but we know what 2x is equal to because we can do the math, right? So we know 2x is equal to 2.5 because that's how we got from 3 to 0.5. So what is x equal to? 1.25. Aha! We have now solved pretty much the entire problem. That's the hardest part, is figuring out what x is. Okay, I lost you. Okay, if I know that, if I didn't know the numbers here, I would have to just plug in x's, right? Since I have a coefficient of 2 here, I have to implement it here because it's a stoichiometric ratio all the way across. So really, I know that it doesn't tell me that I start off. I'm going to fill in this chart in a second. It doesn't tell me I start off with any product, so I'm going to assume I have 0 and 0 of both of those. And before I plug in true numbers, let's just plug in x's. So if I minus 2x from this side, what am I adding here? Also a 2 because there's a 2 in front there, so adding 2x, I'm using the coefficients, and adding what here? Just 1x, right? So plus 1x. So I'm going to put those in parentheses because that's my guidance. I kind of use that to guide me through the problem, but I don't actually plug in x's there. I know for sure what x is because I can do easy math. 3 minus 0.5 is 2.5, and then divided by 2, x is equal to this. So I know I'm subtracting 2.5 here. What am I adding here? How do you know it's 2.5? X times 2, right? We know what x is right here. So I'm adding 2.5 here. What am I adding here? 1.25. So the hardest part is just figuring out what x is, and then you just roll with it. You just minus it from some sides and add it to the other sides. So this is equal to 0 plus 2.5 plus 2.5. 0 plus 1.25. 1.25. All right, now I've got my equilibrium stuff. What do I do now? All right, what's my KEQ equation first? So O2, okay, concentration. What's the next one? I don't get to multiply by 2 NO squared. I do not get to implement the NO on the inside. I mean the 2 on the inside. I have to implement on the outside the exponent. And then NO2 squared. Okay, so now I get to plug in numbers, and this part's easy. O2 is 1.25. NO is 2.5. Don't forget to square over 0.5 squared. I don't know what that number is. It's whatever it is. 32, 31, 31.25. So it's not like hard, it's just kind of tedious to get through and say, how do I do this problem? I know this much, what can I do with this? You have to know what these pieces of information, what they give you, you have to know how to use them. Okay, all right, can I do number 6 now? Have you started it? Set it up for a second. I'm going to write up the information on the board. Awesome. We're still reviewing from last week. This is great. That's fine. Set up number 6 for yourself. I'll check Jake. I believe him. I'm just going to double check that. So you put 1.25 times 2.5 squared in parentheses divided by 0.5 to the second in parentheses. I got 31.25. What'd you do? Did you plug in calculator wrong? That's probably what you did. You need to square everything and then divide. Alright. 7 or whatever. 6. Okay, you've got your reaction of hydrogen gas plus iodine gas equilibrates to 2HI gas. This is a good one. I think I actually put this exact formula on there. Oh, no. If the initial concentration of H2 was 0.02, where do you put that? In the I of ice, H2 is 0.020 molar. And the I2 is 0.04 molar. Calculate the K if at equilibrium the original concentration of H2 was reduced by 0.01. So what does that tell you? So they're telling you it's changing by 0.01. Alright, so we've officially said we know what X is, right? Because this is, if you didn't know the change, you'd have to call it 1X because of the 1 coefficient up here. So we know that X is equal to 0.01 because that's the same as what we subtracted. So let's go ahead and fill in the X's all the way across and then we'll do equilibrium. What do we start with here? 0. What do I minus here? Okay, so I would minus 1X, right? But 1X is equal to the same number. So minus 0.01. What would I add here? Yes, so I would essentially be adding 2X over here because there's 2 coefficient. But I do know what X is, so I'm going to add 0.020. Alright, so then this one is 0.010 left. This one is 0.030 left. And this is 0.020. These are all molar, of course. So these are concentrations. And then what do I get to do? Plug it in, plug it in. What's my KEQ expression? HI squared times I2. Awesome. So then HI squared is 0.020 molar squared over 0.010 times 0.030. And then plug in your calculator and go. Now you see I'm writing down every thought and work and unit and everything in these problems. You don't have to write down like we know when you square root x and you have to go through like 5 steps to solve for x. You don't have to write down every step for solving for x, but this is essential. I need to give you points for your BC, I need to give you points for your icebox, I need to give you points for setting up your KQ, and I need to give you points for plugging them in, I need to give you points for your answer. So do walk me through it, and just assume that I need you to write this down for me. Yeah.
So you do have to write out the kind of the variable equation.
I mean, usually I ask you to in the problem, or at least set it up, because what people do is they automatically plug it in, and then like everyone does is they forget to square or cube or whatever they have to do. So if you set it up and you write it once, you won't forget to write it the second time. It just sets you up for success. I'm trying to set you up for success. Answer? 1.3. Okay, cool. Okay, let's get off KAs and KBs. Let's go to KSPs again. I think it's for all these. Yeah, someplace up here. I'll find it for you. I want to do KSPs real fast. All right, this is the same type of problem. It's just talking about something different. What were our solubility rules way back? Hash and Gia. Who were the soluble ones? Hash and Gia. Group 1A and nitrates are all soluble, or ammonia. What were the insoluble ones? Chops. What does each of them stand for? C stood for carbonates, H stood for hydroxides, O oxides, P phosphates, S sulfides. There's a lot of things that are insoluble. What's a common name for something that forms solid in a reaction? Precipitate. All right, so when two things come together, they make a precipitate, and it's a solid. Does any of it dissolve at all? All right, if a precipitate forms, you put two things together and you see a solid forming, does any of that solid precipitate dissolve at all? Okay, essentially no, right? Because it's whatever does dissolve is so itty bitty bitty. We just say nah, it's gone. None of it at all dissolves. But truly, when this like blob forms and water is surrounding it, water forces it to dissolve just a tiny bit. Why water? What is water's job? Universal solvent. Okay, that is water's job to pull it to pieces. It's just that these positives and negatives in here are so strongly attracted to themselves that water can't extensively dissolve it. So water can do a little bit of damage around the edges, but not like on the hardcore inside. So water does dissolve it some. And the value that represents the amount that dissolves is called the Ksp value. Okay? So this is what I want you to write down, some of the keywords here on Ksp. What I was just telling you about was this right here. The smaller the number, the Ksp number, means that it has a lower solubility or less of it ionizes / dissolves. So first maybe just write down that about Ksp and I'll scroll back up for you. This is the only slide of notes you're taking. Did you get time to remind you to bring it on?
Like 9:30.
I'll do 5 p.m. You should be home. I'm setting up a scheduled message.
Decent to like
in the
6.
morning at like 6. Like right before we leave.
That'd be
Like to call.
I got 5 p.m. Just hopefully check your phone. Alright, sorry to break your focus. Refocus. Okay. Hopefully you got a chance to copy down some of this. Let me go back up to the top and I'll scroll right back down for you. And as you go through this part, I'm going to explain. So what does the SP stand for in KSP? Solubility product. Okay, this stands for solubility product. What's a product in math? Answer from being multiplied, right? Well, guess what? Whenever you write out this one, you see solid, you see liquid, you see aqueous, and aqueous. What would the Ksp expression be for that exact BC? Concentration of X plus, right, times concentration of Y minus. Well, guess what? It's called the solubility product. It's literally the product of the concentrations of the two things that are dissolved. So when it says solubility, it's talking about the ions dissolved. When it says product, it means like multiply those babies, and then they're done. Because the pure liquid and the pure solid are irrelevant here. So every Ksp will be set up like that with no denominator. Because how do things dissolve? What do they come from? Well, water helps, right? But what do things, they come from a solid. They come from a solid piece that goes into water and breaks apart. So every Ksp will not have a denominator. All right, so the product of two ions in the mixture, okay, this is what I have to say about this. Sometimes we can add just a little bit of both reactants together. And that small amount that's in there will not cause a precipitate. But if I put like two dump trucks of things together, I'm probably going to see a precipitate. Because it's just, there's so many ions in the solution that almost like they're super saturated and they just drop out. Remember, if you in a super saturated solution, if I disturbed it, it would precipitate out. Or if I put just like a seed crystal in there, which is what we're going to do with the rock candy, it will precipitate out. It's the same story. Too many ions in solution is very unstable and they precipitate out. So if the product of two ions is greater than the Ksp, I'm going to give this bolded thing here a name. The product of the two ions I'm going to call Q. So the rule is if Q is greater than Ksp value, then the ions are just, there's too many in the solution, so they have to precipitate out. I'll tell you how to calculate Q. It's the same way we've been doing, but I just want to show you. So there will be a precipitate that forms. We refer to this number as Q. So I'm going to walk through this. If I put 0.0001 molar of silver in solution, and I put 0.001 molar of chloride in solution, usually silver and chlorine come together to make silver chloride. But if there's not enough of it, I want it to form a precipitate, that's my goal, but there's just not as many ions in solution, so they will not form a precipitate. So if my Q is less than my Ksp, then there's no precipitate that forms, because there's just not enough ions in solutions. So I'm going to go through two examples with both of these scenarios here. And I'm going to scroll down a little bit so you can see those. So hopefully you got a chance to write down some of that. Yes, Q will be in a literal value. Yep. I mean, Q does have a name. It's called the reaction or reaction quotient. I'm not sure I spelled that right. Quotient. What is it? It looks weird. It looks really weird. It's cool. I don't think anybody knows how to spell it. Right, can I go next page? Okay. I'm trying to make sure we get this, because this is these are, I feel like, sometimes the harder parts of equilibrium. The Ka and Kb, once you get the hang of it, it's not so hard, because you're just doing the same type of problem over and over again. These are just a little different. All right, and I'm going to go to the two questions, or the few questions that are on your worksheet. So, oopsies, so these down here, let's do 5 through 8 here. Okay, so you have your worksheet in front of you, yes? We'll get it out. Oh no, you lost yours. No, we didn't do that 5, we did another 5. Alright, we're going to do 5 on this worksheet. You did 5 on the other worksheet just a second ago. Alright, here we go. Because we've already done 1 through 4. We did 1 and 3 last week. We did 2 and 4 for homework. Number 5, what is the concentration? So as you go through this, write down like your question marks for things that you don't know how to do. What is the concentration of iodide ions in lead to iodide? What is lead to iodide formula? PbI2 is lead to iodide. Good. In a saturated solution at 25 degrees. Saturated means what? It's full of ions. Supersaturated means it's over full of ions. Undersaturated or unsaturated means it's not you can add more and it's fine. So whenever you have an example like this that says saturated, you're going to set up an equilibrium. Because truly what this is a beaker filled with solution, and there's lead 2 plus floating, and there's iodine floating, and there's all these particles floating. But you can have a glob at the bottom, which represents our precipitate. So there's an equilibrium between what's dissolved and what's not dissolved. The way we write that is we've got lead 2 iodide, that is commonly a solid, it's a precipitate, and a smidgen, just a little bit of that, will dissolve to make what ions? To make what ions? Lead, what? Lead 2 and, just lay them on my desk, I'll get them. Just lay them on my desk.
There's only one.
Okay, just lay, I got it, thanks. And 2 I minuses, right? Alright, and these, when they dissolve, are aqueous. I need your focus because I need you to work with me through this because this is one of the harder problems. Alright, so this equilibrium set up because solid can dissolve just a teeny bit of it. This right here, I'm sorry, the Ksp for this is what? 2.4 times 10 to the negative 4. Does that mean it's soluble or insoluble? Look how small that number is there. Okay, hold on, let me go through this. What if I say a small Ksp to a large Ksp? It ranks the solubility. If you have a large Ksp, that means that no precipitate will form, it's very soluble. A small Ksp means that a precipitate will form and it's very insoluble. I mean, true, this is to the negative 4th, that's not that tiny. There's some that are to the negative 31. Like 10 to the negative 30th might be over here. 10 to the 30th might be over here. So it's, you know, in the middle, that's like kind of soluble. There you go. Very technical word. That's 10 to the negative 4th. So there is a scale here that represents solubility. Alright, before we start, write out the Ksp expression for this one. Ksp expression. Concentration of Pb2 plus, I hear you, and I minus squared. Anything else? No, because that's a pure solid. These two things are aqueous. So this right here, this expression equals 2.4 times 10 to the negative 4th, because that's what it said our Ksp value is. Okay, now I'm going to move some of this stuff around so I have some room to write. All right, we're going to use that in a second. We have our BC. We have our setup. Whenever I dissolve some amount of this, how much of the lead is made in terms of X's? 1 X is made. So I can have any number here. I can have infinity there for that. But this is a pure solid and it does not matter. I automatically scratch it out so I don't mess up. Okay? Before this reaction begins, or before this dissolution or dissociation begins, how much of each product do I have? How much before it begins do I have? 0. I start off with 0 and 0 of both products. As the change occurs, how many X's get added to PB? 1 X gets added to PB. How many X's get added to I? 2X. Okay, so then in the end, I just get X and 2X. So I sometimes will set up a nice box for this because it's like, I can do that in my head. I can just set up an E if I want to. Just go straight to E if you want. But that's because you know that you can start off with 0 of all your products. Okay, so those X's go where? In this expression, right? So this will be, nope, not quite. Inside of the PB box, I have X. Inside of this box, I have what? 2X squared. So that's why I like for you to write out your equilibrium expression first, because that means you'll never forget to put a squared there. But commonly people forget to put this X or this squared over here. So I like you to write it out first. All right, so then simplify that for me. Simplify this green right here. Let's try again. 4x cubed, thank you. So 2 has to be distributed in. So 2 times 2 is 4. So then we have x here, we have 4, and then the 2 also gets distributed to that x. So that's 4x squared. X times x squared is 4x cubed. Okay, so 4x cubed is equal to this number, 2.4 times 10 to the negative 4. All right, what's next? How do I solve for x? Huh? Not yet. Let me go ahead and divide by 4 first. Divide by 4 on this side. Divide by 4 on this side. 6 times 10 to the negative 5th. Let me verify that for me. I could have mine worked out, but I don't.
Yeah.
Okay. X cubed. Cube root of that. Can't do that one. What's cube root of that? 0.039. So let me verify too. I like have multiple calculations. Okay. So we just got x to be 0.039. And then you go, okay, what was our question, Miss Inline? What's our question? What's the concentration of I? So let's go back to the ice box and look. What represented I? 2x. What did we just solve for? X. What do we need to do? Multiply by 2. Okay? So plug that x in. So we got like 0.078. So 0.039 times 2. So I just solved for x. X was just old x. That's x for you. And then the question was to solve for iodine. Well, iodine at equilibrium is 2x. So when you solve for x, you need to go back and look at your question and say, what am I supposed to be doing with x? We needed to multiply by 2 to solve for the iodine concentration. So that was at equilibrium, answer. At equilibrium, it is 0.078 molar. So I took x and I multiplied by 2. Yeah.
So the pH just refer to the K.
Yeah, pH is only with acid-base Kas and Kb's. KSP, usually you're going to be solving for x and then do something with it. Yeah. Because at equilibrium is literally what the ice box says. The squared part comes in because that squared part comes into solving for KSP. That's the only time you ever square it. Since it's not specifically referencing KSP, it's representing the equilibrium. You can go to the ice box to see what represents I or X. All right, long problem. Ready for next one? Yes. Yes, thank you, Kathan. Kathan's ready. All right, let's do number 6. I'll give you a stretch break after this one. What is the molar concentration of calcium? Oh, I'm sorry, number 6. What is the molar concentration of silver chloride? What's the formula for silver chloride? AgCl, okay. At 25 degrees C, KSP is equal to 1.6 times 10 to the negative 10. All right, on the scale, soluble, insoluble, very insoluble, what? Very insoluble. More or less soluble than the previous example? Less, I'm sorry, that's more insoluble. So it's more insoluble, but it's less soluble, okay? So you can rank things like soluble, kind of soluble, and then very insoluble. We can rank these based on their KSP values. All right, first thing we did last problem was what? Set up the BC. What's the BC for this one dissolving? AgCl, solid, liquid, what? Solid. Equilibrates to? And these are both aqueous. Aqueous. Okay.
Why would the scale be 2?
Because this is in water. In water, things ionize.
So it doesn't matter.
Only when it's a gas will you put chlorine gas. This is ionizing in water. And sometimes people put water above the arrows like that, but I'm not. All right. I set up an ice box. Oh, no. What did I do next? I did my KSP. So I'm trying to give you a method here. Set up your BCE. Leave some space for an ice box because you know you're going to have to do one. KSP. What is my KSP expression for this reaction? Ag plus times Cl minus. Good. Equals to the 1.6 times 10 to the negative 10. Okay, now I get to set up my ice box. Notice, like, these types of problems are really, they're not bad because they have no numbers in them except for the KSP value, and that's it. Then you just get to plug in x's and then solve for x. So you don't have to, like, figure out where to put a number because there's no numbers given to you. So this one says solve for molar solubility. Write this down. Molar solubility means solve for x. That's all I mean by molar solubility. So I can give you solve for molar solubility of dinosaurs. That means I want you to solve for x. Okay? So note that's just a note you need to know. So our goal here is to solve for x. Icebox, What did I ignore earlier? Solid, so I just put a big scratch through it. And then you say, how much do I start off with the products? 0, 0, plus x here, plus x here. I end up with all of, you guessed it, x and x. All right, what do I do with those? Okay, so I'm plugging them in where? Right, so the KSP gives me AG to the first power, CL to the first power. So that's just going to be x times x, which is x squared. How do I solve for x? Square root, so 4 times 10 to the negative 6. Somebody tell me if that's right. 4 times 10 to the negative 6. Okay, yeah, that wasn't right. 1.2 times 10 to the negative 5th is equal to x. And that equals to molar solubility. And that's molar, by the way. Molar. Yay! After you get through Ks and Kbs, this is not so bad. Alright, I want to do one where you have to compare the K or the Q and K. Number 8. So I'm going to skip to number 8 and we'll skip 7 for a moment. Actually, stretch break real fast. Stretch break, I'm sorry. Go visit somebody you haven't seen in a while. See how the weekend was. We had an email earlier. Okay, ready? Work with me. Work with me. Will a precipitate occur? So this is the time where you have to compare Q to K. And these are a couple things you might want to write down at the top of this paper or wherever. When Q is greater than KSP, what did I tell you occurred? Precipitation or no? Which one? PPT will form. Okay, this is PPT. Essentially, that means it's super saturated. So this is a key to how you interpret Q's versus K's. If Q is less than KSP, what do we say? No PPT, and we said it meant unsaturated. Good. If Q is equal to KSP, it is at equilibrium. And what do you think it is? Out of these choices, it's just saturated. Okay, so that's what the K and KSP stuff means when you actually talk about it in terms of like qualitative reasoning. All right, so now the question. Will a precipitate occur when 50 milliliters of 0.025 molar strontium nitrate formula? NO3 2, thank you, because strontium has a 2+ charge. When that is mixed with 50 milliliters of 0.014 molar solution of copper 2 sulfate, what's that? Beautiful. 2's and 2's. 2 plus 2 minus. Okay. The KSP for strontium sulfate. So it's telling us our KSP for what? What's strontium sulfate? Is it ST or SR? I always mess it up. It's an R. I continually put T. It doesn't matter what day it is. I'll wait. Okay. Go ahead. Okay. So this is what I'm writing it for. This is neither one of these. So that means I'm probably going to have to write out a what? BC. Okay. So the KSP they gave us was 3.2 times 10 to the negative 7. All right. So first of all, you should be knowing or noting to yourself, when I ask if a precipitate will form, it means that you have to solve for Q. Because how else are you going to solve or compare Q's and KSPs if you don't at least solve for Q? Right? So they've given us the KSP value. We're good there. We need to find Q. Well, Q is calculated exactly the same as KSP. So if I told you to write a KSP expression for me right now, what would you have to write? KSP expression for this thing that they've given us the KSP for. Concentration of SR charge? 2 plus, and concentration of Nope, not this one. This is the KSP they gave us. SO4, charge 2 minus. Alright, so you know you can do that basically from the simple fact that this right here, strontium sulfate, assuming it's a solid, will dissociate into what and what? SR2 plus aqueous and 2 minus aqueous, okay? So that means that this solid makes those 2 ions. And that's, we have to write it like this because that's literally what they told us the KSP they were referencing is 4. So that means before this whole thing happened, we formed a strontium sulfate product. Well, how do we form this strontium sulfate product? We put strontium nitrate and copper 2 sulfate together. What's that BCE? Yes, I'm going to write it. I guess I'll write it here. SR, okay, yields, plus yields, and, right, and that 2 balances that one, we're good. Alright, so instead of, listing it with the volumes and molarity like that, they could literally say that these 2 things react and they make a precipitate or make strontium sulfate, and you have to decide if it's going to precipitate or not. So they could phrase it a little bit differently, but this red and this up here is the same. It's the same exact problem. All right, so we have to figure out from these 2 things up here if they make enough concentration that when we plug it into the KSP or the KSP expression, it makes a situation where Q is greater than K. So we just wrote out the KSP expression like that. I'm going to erase the KSP there, and I'm just going to put Q. Q and KSP are calculated exactly the same way. So I don't want you to be like, oh, I've got this new awkward variable I don't know what to do with. It's literally set up exactly the same. I need to get concentrations for this, though. So you see they gave us concentrations, right? Of both strontium and copper. Strontium and sulfate, essentially. But that would be way too easy for us to just look at, oh yeah, let's just plug it in. Okay, so that means that we have to use these volumes some way, somehow. Do you remember in our acid-base mixtures when it gave you like 2 strong acids, you had to find the moles of moles of H plus, and then divide by total volume to get the new H plus? Maybe? Okay, we're going to do exactly the same thing, it's just not with H pluses this time. So these 2 things I'm going to pull down here so I can use them, because I got to do some calculations. Okie dokie. Alright, so let's calculate how much of the strontium, I'm so not good at this right now, how much of the strontium we have, and then how much how much of the strontium and how much of the sulfate I have. So to get the strontium, I have to do M times V divided by total V. That's it. What's my M times V for this one? M is 0.25 molar. I'm just going to put moles per liter times my volume, but I need to change that to liters if I'm only using liters here. So what's that in liters? 0.05 liters, right? So check, I've used both of those. That's going to give me moles because my liters and my liters cancel. I should probably be calculating for you guys. Let me write down. So that's 1.25 times 10 to the negative 3 moles. I like scientific notation, sorry. Alright, and then I need to divide by my total volume. What's my total volume? 100 milliliters, so 50 and 50, so 0.1 liters, right? So that divided by 0.1 is 1.25 times 10 to the negative 2 molar. Molar. So if you don't like scientific notation, just move the decimal back. So 0.0125 molar. Yeah.
So did you get that liter on the bottom?
I took my total volume of this plus this to give me 100 milliliters, and then I just divided by 0.1 to be 100. All right, so here we go. Here's SR2 plus. Let's do exactly the same thing with, what's my other ion of interest? SO4, right. So sulfate, same thing. What's my molarity and volume? 0.014 moles per liter times what? Yep, 0.050, which was my 50 milliliters sample. It told me it had Liters and liters cancel. That gives me 0.007, something like that. I can't work my calculator right now. So 7.0 times 10 to the negative fourth moles. And then what did I have to do previously? Okay, divide by, what's my total volume again? 0.1, because it's still 100 milliliters. So that divided by that is 7.0 times 10 to the negative 3 molar. Oh. I'll go back and trace you through it. This is equal to SO4, 2 ions. Right, these are the 2 ion concentrations you plug back into the Q. And then you look at the Q and you say, is this number bigger than KSP, yes or no? So these 2 numbers I'm plugging into my Q expression. My Q expression wasn't exactly the same as the KSP expression though. It's just that times that, so strontium times sulfate. So 0.0125 molar times 0.0070 molar, which is what this is. So those times one another, 8.75 times 10 to the negative fifth. All right, look at your KSP value that's on your paper someplace. Is that number bigger or smaller than the KSP on your paper? All right, it's bigger because it's less zeros in the front, right? So it's 0.0000875, whereas the one on your paper is 0.0000032. So this is bigger, so what happens? Super saturated and it forms a precipitate. Huh? So yes, the precipitate forms. You have to show me your work for support, because you can easily guess that.
Please pardon the interruption. Please dismiss all seniors to the football field. Seniors, please bring your things with you to the football field at this time. Thank you.
She's not a senior, guys.
Oh, it's like,
No. Okay. That's the one that I'm doing for now. You guys have to do number 7, and then you can start on your problem set 18 and ask me some questions. Huh? Number 7 is not a long one like that. Okay, I'm gonna scroll back up and walk anybody through it who wants it. Oh, I had one for you on Friday, and then you left. It says, but it doesn't. Oh, I think doesn't it say salt for KSP?
it says that 5 degrees Celsius.
Hold on, does it say salt?